So in a previous lecture, we discussed how to solve a PDE using the separable variable method. Also, we discussed two examples. One example is the first order PDE and second example is second order PDE. Now in this lecture, we discuss a one dimension heat equation, how to convert. Also we discuss how to convert any problem in mathematics form, and then how to apply a separable variable method in initial and boundary value problem. So first we discuss problem 1. Problem 1 is based on heat conduction in a bar with homogeneous boundary. So in a one dimension heat equation, mainly two types of problem is arrived. One is a heat conduction in a bar with homogeneous boundary. Homogeneous boundary, that means whose both ends are held at zero temperature. This is called homogeneous boundary. And the second problem is heat flow or heat conduction in a bar with insulated ends. Insulated ends, that means heat is not flow in both ends. That means a constant temperature. So now first we discuss a heat conduction in a bar with homogeneous boundary. So now we consider a simple problem of heat conduction in a length L. See the figure, length L, whose both ends are held at zero temperature. So we consider one heat conduction bar, that means rod, whose length is L, and both ends are held zero temperature. Thus, the initial boundary value problem is given as del U by del T is equal to C square del square U by del X square. This is the one dimension heat equation. So any problem which is based on heat conduction in a bar, then we use the one dimension heat equation. Now in this problem, the rod length is L. Rod length is L. Rod length is L. So this in the left ends and this is the right ends. So there are two required boundary conditions. And one require initial condition. So now we solve this equation. So the two require boundary condition and one is a initial condition. Here in this problem, the boundary is homogeneous. Therefore, the both ends are held zero temperature. Also, the expression of this equation, u is a dependent variable, x and t is an independent variable. So u is a function of xt. So uxt is indicate a temperature at time t and space x. So x indicate space, t indicate time, and u of xt indicate the temperature at time t and space x. So now the rod length is L. So in the left ends, the temperature is 0. So the boundary condition is defined U 0 T is equal to 0. Here the value we consider x is equal to 0. And the right ends, not left ends. Here ULT is equal to 0 means x is equal to L. So this is the left end temperature. This is the right end temperature. And both ends are held 0 temperature. So the boundary condition is defined U0T is 0 and ULT is 0. And the initial temperature in a bar is Fx, we consider. What is the meaning of initial temperature? So we consider when time t is equal to 0, then the value of u, that means the temperature value, is called the initial distribution temperature in a bar. And we consider the value is Fx. So only one initial condition, so t equal to 0. When t equal to 0, the temperature ux0, which is called Fx ux0 is an initial distribution of temperature. So again, I repeat a total problem. One dimension heat equation. There are two types of the problem. Problem 1 we discuss heat conduction in a bar with homogeneous boundary. That means both ends are held 0 temperature. So the initial boundary value problem is given as one dimension heat equation. First we write two boundary condition when x is 0, that means left ends of the rod temperature is 0, that means u0t is equal to 0, and right ends when x is equal to L, so ult is also 0. And the initial temperature in the bar, we consider the function fx, therefore ux0 is equal to fx. Again, uxt is indicate a temperature at the time t and space x. So x is a space and t is time. Now we solve this problem. So first we solve equation 1 using a separation of variable methods. So in a previous lecture we discussed how to solve any PDE using a separation of variable method. So first we consider a solution form. So here x and t are independent variables. So uxt is equal to x of x, t of t. Capital X is a function of x, capital T is a function of t. So we consider equation. Now differentiate equation 1 2 times with respect to x and 1 time with respect to 2. with respect to T, because here the equation is a del u by del T. So we find del u by del T, we find del square u by del x square. So del u by del T, that means differentiate this equation with respect to T but one time, and this equation differentiate with respect to x but two times. So we get del square u by del x square is a x double dash T, and del u by del T is a x T dash. Obviously x double dash is a second order OD, del square x capital upon dx square, and T dash is a dt by dt, capital T by small t. So therefore the given PD is a reduce del u by del T, that means xt dash is equal to c square x double dash T. And that implies we use the separable of variable method, so we separate both variable. So we write x double dash upon x is equal to T dash upon c square T. Obviously equation 2, whose left hand side which is depends only on x, right hand side which is depends only on T, and left hand side is equal to right hand side for all T and x. Therefore we consider both sides equal to the constant k. So we get a two ordinary differential equation. One is x double dash upon x is equal to k, and another T dash upon c square T is equal to k. So this is equation 3. Now in again previous lecture we discuss if the second order OD is arrived, then we consider a different types of case. One is a k greater than 0, k less than 0, and k equal to 0. And each cases we find the solution of the given initial boundary value problem. So first we consider k greater than 0. So obviously k is equal to, we consider p square, p not equal to 0. Then equation 3 become x double dash minus p square x is equal to 0. Auxiliary equation is m square minus p square is equal to 0. So m is equal to plus or minus p. This is real and different root. So we write x of x is a c1 e raised to px plus c2 e raised to minus px. But in a second order, in a second OD, we write t dash minus c square p square t is equal to 0. This is not a second order OD. This is a first order OD. So obviously we get m is equal to c square p square. Only one root, and this is real root. So we write t of t is equal to c3 e raised to c square p square t. And we combine both because the solution form is a uxt is equal to x of x, t of t. So x of x and t of t. So c1 e raised to px plus c2 e raised to minus px into c3 e raised to c square p square t, where c1, c2 and c3 are arbitrary constant. Now this is the first solution of the given initial boundary value, so of the given partial differential equation. We applying a boundary condition, that means equation 2. We applying the boundary condition, that means this is the boundary condition 2, 3 and 4. So now we applying the boundary condition equation 2. The boundary condition is when a temperature is 0, when x is 0. That means left and temperature. So u is 0 when x is 0 in the given equation 5. that means the previous equation. So x is 0, that means here we write x is 0, x is 0. So we get 0 is equal to C1 plus C2, and this term as it is, because this term is not depends on x. So therefore C1 plus C2 into C3 e raised to c square p square t is equal to 0. That implies 0 is equal to C1 plus C2, and this term is the solution of T of t. So implies T of t we can't consider 0. So therefore C1 is equal to minus C2. Because if we consider T of t is equal to 0, then directly we get uxt is 0. And uxt is 0, that means the trivial solution. So we can't consider T of t is equal to 0, then we get C1 is equal to minus C2. Now we input C1 is equal to minus C2 in equation 5. Then the equation 5 become uxt is equal to C1 e raised to px minus e raised to minus px into C3 e raised to c square p square d, which is called equation 6. Now again we apply the second boundary condition, that means equation 3. And the boundary condition is when x is L that means right ends, the temperature value is 0, u equal to 0. So x is L, u is 0, we get 0 is equal to C1 e raised to PL minus e raised to minus PL into this term again as it is. So implies 0 is equal to this term into T of t. So again T of t not equal to 0, because if we consider T of t is equal to 0, then a trivial solution. So T of t is not equal to 0. C1 we can't consider 0, because if we consider C1 is 0, then C1 is equal to C2, we know that minus C2, that means C2 is 0. So C1 is 0, implies C2 is 0, and then x of x is 0, which leads to the trivial solution. Also, e raised to PL minus e raised to minus PL also not equal to 0. The reason is P is always greater than 0 for this case. L not equal to 0 because length is not 0. So this term is not 0. We can't consider C1 is 0. And also we know that T of t is not equal to 0. That means this term is not equal to 0. But here this term is equal to 0. Hence, non-trivial solution of equation 5 does not exist, which are satisfying the given boundary conditions. So we can't consider the case k greater than 0 for the solution of this problem. So for k greater than 0, the non-trivial solution is not exist. Now we discuss k less than 0 case. So k less than 0, obviously we consider k is equal to minus p square. Then 2 OD obtain x double dash plus p square x is equal to 0. whose auxiliary equation is m square plus p square is 0. So we get m is equal to plus or minus pi. Now this is the complex root. So we write x of x is equal to c1 cos px plus c2 sin px. In a second OD, t dash plus c square p square t is equal to 0. This is a first order OD. So m is equal to minus c square p square. Then the solution is a t of t is equal to c3 e raised to minus c square p square t. So x of x, t of t is defined. We input in a general solution uxt of x of x, t of t is equal to c1 cos px plus c2 sin px, c3 e raised to minus c square p square t. So this is equation 7. So equation 7 is a solution of the given problem, one dimension heat equation when k less than 0 case. Now similar procedure for case k greater than 0. We applying the boundary condition equation 2. When x is 0, the temperature is 0. In equation 7 we get, so we apply here u is 0 when x is 0. So 0 is equal to cos 0 is 1. So C1 sin 0 is 0. So this term is 0. So we write 0 is equal to C1 into C3 e raised to minus c square p square t. Again C3 e raised to minus c square p square t is nothing but t of t. T of t never 0, because we consider equal to 0, that means u is equal to 0, which is not possible. Therefore we consider C1 is equal to 0. So now we input C1 is equal to 0 in the previous equation number 7. Then equation 7 become uxt is equal to C1 is 0. So uxt is equal to C2 sin px into C3 e raised to minus c square p square t. So this is equation 8. Again we apply the another boundary condition, that means equation 3. Which one is, when x is L, the temperature u is 0. So in equation 8 we apply x is L where u is 0. So u equal to 0, C2 sin PL, C3 e raised to minus c square p square t. This term is as it is. So implies 0 is equal to C2 sin PL. This is t of t. Again t of t never 0. C2 also not equal to 0. Because we consider C2 is 0, then x of x is 0. And x of x is 0, that means u is 0. So we consider sin PL is 0. So now 0 is equal to C2 sin PL into t of t, where t of t and C2 not equal to 0, therefore sin PL is 0. Sin PL is 0, that means PL is equal to n pi, and therefore P is equal to n pi by L, where n is 1 to up to n. So we get P is a n pi by L. This value we input in equation 8. Then equation 8 become uxt is equal to C2 sin n pi x by L, C3 e raised to minus c square n pi by L whole square into t. And hence also we can say the solution of equation 1 is satisfying the boundary condition. So for k less than 0 case, the solution uxt which is satisfied a boundary condition. And we get uxt is equal to c2 sine n pi x by L c3 e raised to minus c square n square pi square by L square into t. Now c2 into c3 is a constant, so we consider bn, and n is 1, 2, 3 up to n, so on. So we write this form is bn sine n pi x by L e raised to minus c square n square pi square by L square into t. Now applying the superposition principle, the solution of equation 1 satisfying the boundary condition is given by uxt is equal to, we apply the summation n is 1 to infinity bn sine n pi x by L e raised to minus c square n square pi square by L square into t. Equation number 9. Now we consider case 3, k equal to 0. K equal to 0, then obviously we get two ODs, x double dash 0, t dash 0. So m is equal to 0 2 times, which is auxiliary equation. Then we get x of x is a c1 plus c2x, and here t dash is 0. That means the solution of t is constant c3. Now we combine both. Then the case k equal to 0, the solution of one dimension heat equation is uxt is equal to c1 plus c2x into c3. Now same procedure we apply the boundary condition for this case. So first we apply x is 0, implies u is 0. So x is 0, u is 0. That means equation 10 become c1 into c3 is 0. So obviously c3 is a constant, c3 is the t of t. So c3 not equal to 0, therefore c1 is 0. Because t of t we consider not equal to 0 because u is 0, which is not possible. Hence the equation 10, not 7. Hence the equation 10 become uxt is equal to c2 into c3 into x. This equation is 10, not 7. Again we apply the second boundary condition. X is L when implies u is 0 in equation 11. So 0 is equal to c2 c3 L. Now 0 is equal to c2 c3 L. We know that L not equal to 0. We can't consider c3 is 0. And if we consider c2 is 0, then this term is 0. That means x of x is 0. That means we can say c2 not equal to 0, c3 not equal to 0, and L not equal to 0. Hence, non-trivial solution of equation 5 does not exist for k equal to 0. Non-trivial solution of equation 5. Does equation 5, that means a solution of one dimension heat equation. Non-trivial solution of one dimension heat equation does not exist for k equal to 0, which are satisfying the given boundary condition. So generally, first we apply the separable variable method in a one dimension heat equation. We get three different solutions. For k greater than 0, we get uxt, one solution, k less than 0, and k equal to 0. Now in each case we also apply the boundary condition. But for k greater than 0 case and k equal to 0 case, we can't get a non-trivial solution of the given problem. So again I repeat, k greater than 0 case we get trivial solution. K equal to 0, we get trivial solution. So only one case, K less than 0, where non-trivial solution is exist, and also a solution is satisfied a boundary condition. So thus, the only one solution occur of equation 1 satisfying boundary condition equation 2 and 3 is given by uxt is equal to summation n is 1 to infinity bn sine n pi x by l e raised to minus c square n square pi square by l square into t. So this equation 12 is a solution of one dimension heat equation at any time t and space x. Again, equation 12 is the one dimension heat equation solution which is define a temperature U at any time t and space x. Now in equation 12, we find the value of Bn, we apply the initial condition. The initial condition is given when time t is equal to 0, the temperature U is equal to Fx. So we apply U is equal to Fx when time t equal to 0 in equation 12, we get Ux0 is Fx is equal to summation n is 1 to infinity Bn sine n pi x by L. E raised to 0 is 1. So we get equation 13. Now equation 13 is nothing but a half range sine series expansion of Fx in the interval 0 to L. Therefore, the Fourier series coefficient Bn is defined as Bn is equal to 2 by L 0 to L Fx into sine n pi x by L dx, where n is 1, 2, 3 up to n. So finally, the solution of one dimension heat equation with boundary condition and initial condition is uxt is equal to summation n is 1 to infinity Bn sine n pi x by L e raised to minus c square n square pi square by L square into t, where Bn is equal to a half range sine series coefficient. So 2 by L 0 to L Fx into sine n pi x by L dx. So equation 12 is the solution of heat conduction in a bar whose both ends are held 0 temperature and the length of the rod is L. Also, Fx is a initial distribution of temperature. So thank you. Now in the next lecture, we discuss an example of a one dimension heat equation with homogeneous boundary conditions.